Okay, let's unpack this. Imagine for a moment you're a developer, or, even just someone looking for a useful software tool, or maybe a helpful script. You go to a place you trust, right? A major code repository platform that thousands, millions maybe, rely on. You find a project that looks popular, seems active. Maybe it's exactly what you need, so you download it, maybe even compile it. You're thinking, great, safe open source code.
Yeah.
But what if instead you've just opened the door, let a threat actor right onto your machine?
Yeah, it's a chilling scenario, but unfortunately, it's becoming a stark reality in the digital world. Even these platforms we trust for building and collaborating, places like GitHub, they're being actively exploited. They're becoming vectors, harboring hidden dangers that are camouflaged, made to look totally legitimate.
And that is precisely what this deep dive is all about today. We're exploring how these threat actors are, well, weaponizing code repositories. Specifically, how they're manipulating the very signals we all rely on to, gauge trust and popularity. They're hiding sophisticated malicious code right out in plain sight. And they're not just targeting who you might expect.
No, exactly. We're talking about campaigns designed to infect, well, pretty much everyone, from seasoned developers, security researchers looking at code, all the way down to casual users just looking for things like, say, game cheats.
Yeah, we've been looking at some pretty in-depth reporting and analysis detailing these recent discoveries, this malicious activity targeting users of open source code.
And it's not simple stuff either. It's layered. Clever social engineering mixed with technical tricks designed to deceive on multiple levels.
So our mission today is to take you through the details. We need to unpack exactly how these deceptive tactics work, understand who's being targeted, which is, frankly, surprising. Reveal the complex, often multi-stage ways this malware is hidden and distributed.
Yeah.
Explore what might be behind it, like is there an organization, a business model? And most importantly, discuss what this all means for you. What are the key takeaways, the critical things you absolutely need to be aware of right now?
Definitely. And before we really dive in, we want to mention that this deep dive is sponsored by Stonefly.
That's right. Stonefly is a recognized leader in enterprise storage solutions. They cover, well, pretty much everything from backup and disaster recovery to AI storage and cloud solutions.
Yeah, and for organizations needing that secure, ransomware-proof storage, Stonefly really specializes in providing air-gapped and immutable storage solutions.
Which, let's face it, in a world with the kinds of threats we're about to discuss, threats constantly evolving, targeting the whole digital supply chain having robust, secure storage is absolutely critical for resilience.
Absolutely. You can contact sales at stonefly.com to schedule a demo with Stonefly.
Okay, so let's start at the beginning. The attack chain, the initial deception. How are these threat actors making their malicious projects look like something you'd actually want to download?
Well, it really begins with exploiting the fundamental ways users search, how you discover projects on platforms like GitHub. When you're looking for something specific, a library, a tool, maybe even just something fun, you use keywords, filter by topics, sort the results. Attackers are creating repositories with names, descriptions, topics that are deliberately very similar to popular, legitimate projects. Digital imposters, basically.
Okay, so they mimic the identity, clone it, almost.
Yeah.
But how do they get these fakes to rank high enough in search for anyone to actually see them? That's got to be key, right? Among millions of repos.
Exactly. Visibility is crucial. And they use techniques specifically designed to artificially boost that visibility, create that illusion of popularity, of activity. One primary tactic, automated updates.
Automated updates.
Yeah. They don't just create the repository and leave it static. They set up scripts, workflows that automatically make frequent, often pretty superficial changes. Could be as simple as writing the current date and time to a README file, committing that change over and over.
So it looks like someone's actively working on it, constantly pushing updates, even if it's just noise.
Precisely. This constant stream of commits makes the project appear actively maintained, recently updated. That boosts its ranking when users sort by last updated. It creates that visual cue, that feeling of a vibrant, living project that developers tend to trust.
And what about the other big signal of trust? The star count on GitHub. Are they messing with that too?
Oh, absolutely. Stars are a huge factor in perceived trustworthiness. And yeah, threat actors have been leveraging fake accounts to inflate star counts for ages. In earlier campaigns, you might have seen them blast a repo with hundreds, maybe thousands of fake stars very quickly.
Which, if you were paying close attention, might look a bit fishy, right? If a project had no real history or contributors. Bit of a red flag.
Exactly. And the analysis suggests they're adapting, they're learning. Recent observations show a shift towards using a more well, a more modest number of fake stars, they seem to be trying to avoid that obvious red flag. An overly inflated count might trigger automated detection or even just manual suspicion.
So they're aiming for a count that looks popular, maybe a few dozen, couple hundred, but not so high it screams fake, flying under the radar.
That's the idea. It shows a clear evolution in their tactics, trying to appear more credible, more organic.
So it's creating this believable facade, fake activity and fake, but not too fake, popularity. And I've heard this star inflation thing is almost like a service you can buy.
Yeah, the whole concept of star inflation is pretty well documented. Previous research has uncovered, online stores, forums, chat groups, specifically advertising and selling GitHub stars. It's a service for cybercriminals, basically. Anyone looking to boost their project's apparent reputation. These trust metrics have become a commodity in the underground economy.
Wow. Okay, so they build these projects, mimic popular names, fake the activity with commits, inflate the stars, maybe just modestly now. What kind of actual content are they putting in there to lure people in once they click?
Well, they're designed to appeal to specific, often quite eager, user bases. The material specifically mentions repositories disguised as legitimate projects, but often in popular niches. Things likely to attract users looking for, quick solutions, performance boosts, maybe a competitive edge in games.
Like game cheats.
Exactly. Popular games, game cheats, trainers, various utility tools. This focus adds another layer of sophistication. Makes it much harder for a user to spot the fake just by glancing at the name, description, and the metrics.
So someone looking for a tool to mod a game, maybe manage crypto, finds a project, looks perfect, decent stars, recent commits, seems relevant. What happens when they download it? Interact with the code, what's the payload?
We can look at one specific example that was observed in the analysis. One repository designed to look desirable, right? It was found to facilitate the download of an encrypted .7's archive file. Inside that archive, an executable file named, very deceptively, feedbackapi.exe.
Feedbackapi.exe.
Yeah, that definitely sounds harmless, like part of some legit software.
Right, part of the social engineering. But what immediately stood out about this executable was its size. It was inflated to a massive 750 megabytes.
750 megabyte for something called Feedback API. That's enormous. Way bigger than any real component like that should be. Why? Why make it so big?
The likely reason, the primary purpose anyway, for this huge size inflation is probably an attempt at antivirus evasion. Some older or maybe simpler AV engines might be configured to skip or just do superficial checks on files over a certain size limit, to speed things up. By bloating the malicious executable, the attackers hope it might just bypass those initial detection scans.
That's a clever, if maybe a bit crude, evasion technique. And what did this massive file actually do when it was run? When executed, this file launched a payload that analysis shared significant similarities with a known piece of malware called the Kizetsu Clipper.
Ah, the Clipper.
Yeah.
Right. For anyone not familiar, a Clipper is designed to steal cryptocurrency, isn't it? How does that work?
Precisely. A Clipper is malware specifically targeting crypto transactions. It sits in the background, monitoring your clipboard. When you copy a cryptocurrency wallet address, maybe to paste it into a payment field, the Clipper detects that specific format. Then, really fast, it replaces the legitimate address on your clipboard with an attacker-owned wallet address, one you never intended to copy.
Ouch.
Yeah. So when you paste the address, you unknowingly paste the attacker's address instead, sending your funds straight to the criminal. And this particular variant, Kizetsu, had been seen before, distributed through things like pirated software, fake versions of Evernote, stuff like that.
That's incredibly insidious. It exploits something people do without thinking copy and paste. Yeah. It hits trust at such a basic level.
It really does. And this whole example, the Clipper payload, the inflated file, the deceptive name, it highlights a critical point, a real aha moment for anyone using open source code. You just cannot, under any circumstances, rely only on a repository's apparent reputation. Star count, commit frequency, popular name, these can be and are being actively manipulated.
So just looking good isn't enough.
Not even close. Genuine due diligence, actually verifying what you're downloading and running, is absolutely essential now.
Okay, so we've seen the fake popularity, the deceptive files, luring users in to drop malware like Clippers. But the analysis also revealed something pretty surprising about who these campaigns are targeting. It's not just the average user, is it? They're almost turning the tables sometimes.
Yes, this is where it gets really intriguing and, frankly, quite ironic. While general users are definitely at risk, these campaigns are frequently, and it seems deliberately, targeting other cybercriminals. Also, people specifically looking for game cheats, and even cybersecurity researchers who might download supposedly malicious code just to analyze it.
Targeting other hackers, researchers. That feels counterintuitive. If you're trying to stay hidden, why poke the bear? Why risk drawing attention from people who know what to look for? How did they figure this out?
Well, the investigation that revealed this often started when researchers began looking into a seemingly open source project on GitHub that claimed to be malware or an exploit tool itself. A specific starting point mentioned was an analysis of a project called cybercrime. Researchers were initially asked to look into it because of claims going around about its, advanced anti-detection
So they
capabilities.
went to check out this supposed piece of malware thinking it was the threat.
Exactly. But what they found pretty quickly was that the cybercrime code itself was largely, well, non-functional, seemed pieced together from copied bits, wouldn't even compile right, wasn't the big threat it was claimed to be. However, the real danger wasn't the RAT's supposed function. It was something much more insidious, hidden within the project files, something designed to infect anyone who tried to compile the tool from the source code provided.
Wait, so the trap wasn't in running the finished program, but in the actual process of building it from the source.
Precisely. And this highlights the really clever technical trick they used. It leverages a standard, totally legitimate feature in development environments like Visual Studio, but also in build processes for other languages. These projects use configuration files like .vbproj for Visual Basic, .csproj for C#, .vcxproj for C++, which let developers define custom actions that happen during the build. One of these is the pre-build event.
The pre-build event. Okay, so that's a command or script that runs before the code even gets compiled.
Correct. It's designed for legit purposes, copying files, generating code, cleaning up directories before compilation starts. It's a powerful feature. But these attackers configured the pre-build event in their malicious project files to execute commands that would silently download and install malware onto the machine of whoever was just trying to compile the project. You hit build in your IDE, think you're just building the tool, but bam, you've triggered a hidden malicious script.
Wow, that is incredibly devious. Weaponizing a standard part of the dev workflow. You trust the build process itself, and that trust gets violated. How widespread was this once researchers started digging?
Well, the investigation into this specific pre-build event backdoor, which was often linked to an email address, is ushefd83trambler.u, found embedded in some config files allowed researchers to trace connections. They used snippets of the backdoor code as indicators, kind of like digital breadcrumbs. Following that trail led them down a significant rabbit hole.
And what did they find down there? More of these.
Oh, yeah. They uncovered a staggering scale to this. Tracing those connections led to finding 141 related repositories scattered across GitHub, and when they analyzed them, a remarkable 133 out of those 141 contained these hidden backdoors. This wasn't just one or two incidents, it was a large, coordinated campaign using this specific technique.
133 backdoored repositories. That's a lot. And these projects were mostly disguised to appeal to those specific groups you mentioned, hackers, gamers.
Exactly. The analysis of the content in those 133 backdoored repos gave a clear breakdown. About 24% explicitly claimed to be malware tools, exploits, attack tools clearly aimed at other hackers or maybe curious security pros. But the largest group, the majority at 58%, were disguised as gaming cheats, mods, trainers, stuff like that for popular games.
And mostly gamers looking for cheats.
Yeah. The rest were things like bot-related projects, about 7%, crypto tools, 5%, and miscellaneous tools, 6%.
So a chunk targeting other cyber criminals, but the vast majority going after game cheaters.
Yeah.
And this puts security researchers directly at risk too, right, if they download this stuff to study it.
Absolutely. If a researcher downloads the source from one of these repos to examine or compile it, even in an analysis environment, they could trigger that pre-build event backdoor. If their environment isn't perfectly isolated and sometimes malware tries to break out, or if they mistakenly compile it on their regular machine, they risk infection. The irony is just profound. Threat actors infecting the tools and cheats used by other threat actors and cheaters. But malware doesn't care why you ran the code. Anyone running it without extreme caution is vulnerable.
It really highlights how pervasive these threats are. Reaching into communities you might think would be more security aware creates a kind of unsettling skepticism for that whole open source spirit, doesn't it?
It certainly complicates things. Trust becomes much harder.
The fact they're embedding these backdoors and targeting niches is fascinating. But reports also detail the sheer complexity of the infection chains. Once that initial backdoor runs, it's not just download and execute, is it?
Oh, not at all. You're right. It's incredibly layered, designed for maximum obscurity resilience. Let's walk through that primary chain, the one from the pre-build event, because it's a perfect example of their multi-stage approach.
Okay, break it down. Stage 1, the pre-build event triggers. What happens right then?
Stage 1 is initiated by those batch commands embedded right there in the project file's pre-build event. The commands themselves are simple, function-wise, but they're heavily obscured, using things like HTML encoding, string manipulation, just to make them hard to read, hard to detect statically. Their only job: write a VB script file to a temporary directory and then run it immediately. Keep the first stage minimal.
Minimal footprint in the project file. Smart. So, tiny obscured script drops and runs a VBS file. Why switch to VB script for stage 2? Another layer.
Exactly, another layer. Stage 2, the VBS script, contains several encoded strings embedded right in its code. The script's job is to take these strings, concatenate them, decode them, write the result into a PowerShell script file, and then execute that. So now we've moved execution to a different interpreter. Potentially evading security tools may be focused only on batch or only on VBS.
Okay, batch to VB script to PowerShell. Layering to make it harder to follow the thread, harder to analyze. What's in stage 3, the PowerShell script? Is it complex?
Stage 3 involves a heavily, and I mean heavily, obfuscated PowerShell script, deliberately made hard to read, hard to understand. Its main job is to decode various strings within itself that contain URLs. Then it fetches content from those URLs. The reports mention examples like arlem.com, popcorn-soft.glitch.me, pastebin.com, pastejustit.com, often legitimate services abused to host malware stages.
Right, using pay sites, cloud services, harder to block because they're generally trusted domains. And the decoding in PowerShell, is it just simple base64 or something more?
It's more. The analysis highlighted a specific decoding function. It combines base64 decoding with an extra step. Character subtraction, using a hard-coded key found right there in the script, adds another layer of complexity for analysis tools or researchers.
So, fetches obfuscated data from these URLs, decodes it using this custom function.
Yep.
Is that the final malware payload yet?
Nope. Still another layer of indirection. The content fetched from those initial URLs after being decoded by PowerShell. Turns out it's yet another encoded string. This newly decoded string then reveals the URL for the next stage payload, the actual malicious file archive.
More decoding, more URLs. Like a digital scavenger hunt designed by crooks.
Oh, yeah.
Stage 4, where's the main malware archive typically hosted?
Stage 4, the payload hosting, is where they often leverage the platform they started on, GitHub itself. The decoded URL frequently points to the main malicious archive, often a 7z file, maybe named search filter pot7z or similar. What's really clever here is that this archive is very often hosted directly within GitHub releases.
On GitHub releases. Wow.
Yeah. And sometimes the repositories used to host these releases were even forks of really old, seemingly legitimate repositories. Probably an attempt to give the malicious release some fake legitimacy or history. Using the trusted platform itself for distribution makes it blend right in.
Hosting the malware right on GitHub releases. That's pretty slick from an attacker's view. It's on a highly reputable domain. Does that 7z archive need a password?
Yes, it does. The search filter.7z archive is password protected, and that password is also obfuscated. But crucially, it's embedded and can be decoded using a key that's hard-coded within the same PowerShell script that downloaded the archive. The script has everything it needs.
Okay. Downloads the encrypted archive from GitHub releases, uses the hard-coded key to get the password, extracts it. Stage 5, what happens then?
Stage 5 is the execution of the primary payload from inside the extracted archive. This is an executable, often searchfilter.exe. Analysis shows it's frequently a very large binary file, commonly associated with compiled Electron applications.
Electron apps. Like the framework used for Slack or VS Code, we've definitely seen Electron becoming a popular way to package malware lately.
Exactly. Electron gives attackers a convenient way to bundle complex code, often JavaScript, into a single executable that runs cross-platform. And inside this searchfilter.exe Electron app at stage 6 is where the core malicious logic really lives. It's typically found within an app.asr file bundled inside the Electron structure. The main malicious code is in a main.js file inside that app.author. And this file, often massive, observed over 17,000 lines long, and yeah, you guessed it, heavily obfuscated.
17,000 lines of obfuscated JavaScript.
Yeah.
Just for the core malware function. That is huge.
Yeah.
Designed to make analysis a nightmare, clearly. What can this thing actually do? What capabilities are packed in there?
The analysis of this core JS malware showed a pretty wide array of capabilities, designed to compromise and persist. Things like system profiling, grabbing detailed info about the machine and user, Command execution, letting the attacker run arbitrary commands remotely, the ability to disable Windows Defender, maybe other security products, deleting shadow copies, that's a common ransomware tactic, right? Prevents easy recovery from backups, creating scheduled tasks for persistence, making sure it runs again after reboot, manipulating registry entries for various malicious purposes. It even had a somewhat crude anti-VM check, just counting CPU cores. Low count might mean an analysis VM, so maybe it stops or changes behavior.
So gets system info, sets itself up to run again, disables defenses, hinders recovery, waits for commands. How does the attacker get notified they've got a new victim? Or send commands?
It includes functionality for exfiltration and notification. It sends basic infection details back, username, hostname, OS info, IP address, sends it back to the attacker.
Yeah.
This communication often happens via Telegram. Using a specific Telegram bot token and chat ID found hard-coded right inside the malware's code.
Telegram for C2, yeah, seeing that more and more. Does the infection stop there? Or does it usually download more stuff?
Often doesn't stop there. After the initial compromise setting up persistence, the script frequently goes on to download and execute additional malware payloads. Specifically, analysis identified it dropping and running potent info stealers and remote access Trojans, RATs, including well-known families like Asyncrat, Remcos, and LumaStealer. These give the attackers deep access for stealing data, surveillance, full remote control.
Wow. So the initial backdoor is just the first domino, kicks off this multi-stage chain, uses legit platform features like GitHub releases, bounces through paste sites, layers of obfuscation, runs a big Electron app with heavily obfuscated JS, disables security, sets up persistence, talks via Telegram, and then drops serious info stealers and RATs.
Okay.
And that's just the primary chain from the pre-build event. You mentioned researchers found other backdoor variants too.
Yes, exactly. This wasn't the only method found among those 133 backdoored repositories. They found several distinct techniques used to kick off the infection. One notable variant involved Python scripts, found in 14 of the projects.
How did the Python backdoor work? Did it also use build events?
No, the Python approach was different, used a really interesting visual trick designed to fool someone quickly scanning the code. The malicious code was in the Python script file, but hidden way over to the right on the lines, using tons of white space. If you don't have horizontal scrolling on in your editor, the malicious part is just invisible off-screen.
Hiding code off-screen with whitespace. That's incredibly simple, but probably surprisingly effective against a quick look in a standard editor. What did the hidden Python code do if it ran?
If the user ran the Python script, it would install necessary libraries like cryptography, Fernet, requests. It used the Fernet library, that's for symmetric encryption, to decrypt later stages during runtime. It would fetch encoded and encrypted stages from URLs, similar domains to the PowerShell chain, Verlim, paste.fo, paste.justit. This chain also ended up downloading and running the same SochFilterPot70's archive. Interestingly, some of these Python scripts had comments in Russian, like manufacturer.unknown. If you've come this far, you have a long way to go. And even a hard-coded 7Z's password right in the code sometimes.
Russian comments. The same password. Little breadcrumbs.
Oh.
What about other methods? You mentioned screensaver files.
Yeah, 6 repositories were found using screensaver files, the .cr extension. These were cleverly disguised to look like .sln files, Visual Studio Solution files. They used the RLO, right-to-left override, Unicode trick in the file name.
Ah, the classic RLO trick. Makes the file name display weirdly reversed, so project RL-on-ls.scr might look like project.sln.resourceace or something, fooling the user about the real extension.
Exactly. Old trick, still works, makes you think you're clicking a project file or document, but it's really an executable screensaver program. These .cr files often had history on VirusTotal, suggesting reuse from other campaigns. They contained a relatively simple backdoor, a big reverse string that, when processed, executed batch commands. These scripts would download files from places like Gilded CDN. Analysis suggests the likely payload here was Asyncrat.
So different methods, but sometimes leading to the same or similar final R8s like Asyncrat. Any others found?
Yes, JavaScript backdoors were also found. In 2 cases, these used techniques like base64 encoding and the evil host function to run decoded code, employed multi-stage decoding, often with the same key vibe.processByUnknown, seen elsewhere, fetched code from similar URLs, urlim, paste.o, pastebin, pastejustice, and also ultimately led to downloading SochFilterPot7sin. Analysis showed older versions of these JS backdoors had used Discord webhooks for C2, sometimes referencing names like Muck or SpideyBot.
Wow, the sheer variety. Weaponizing build events, hiding code off screen, deceptive file extensions, obfuscated scripts. Combined with these complex multi-stage chains, the range of final payloads, It really paints a picture of a sophisticated, adaptable operation.
It really does. They're not just relying on one trick. They're leveraging legitimate platform features, exploiting trust signals using multiple languages, layering obfuscation, building complex delivery mechanisms. This is far beyond trivial malware. It's clearly designed to maximize infection success and make detection and analysis a real challenge. The key takeaway here: interacting with seemingly innocent code from an unverified source can pull you into a very deep, complicated, dangerous process before you even realize it.
And this level of complexity the organization needed, the sheer volume over 130 repos found in one go, it points to something more structured than just one person, right? Feels like a system, maybe even a business.
It absolutely suggests a significant level of automation and structure behind it all. Illustrates the lengths attackers go to create that convincing illusion and operate at scale.
You mentioned automated updates earlier. Is that where the automation is most obvious?
Yes, the heavy use of automation for faking commits is a prime indicator. Researchers found specific GitHub Actions workflow files, usually in the .github workflows directory. This workflow, often named something simple like star, was set to run automatically.
How often was it set to run? Like constantly?
The configuration, using standard cron syntax in the YAML file, was often set for every minute. Now, GitHub Actions has limits, so it doesn't strictly run every minute, but the goal was clearly rapid, frequent execution, resulting in an action roughly every 5 minutes or so.
And the action itself was just writing the date and time and committing. That's it.
That's precisely it. The workflows function was incredibly simple. Grab the current date time, write it to a file like a log or dummy file, commit the change, that's all. The purpose wasn't real development. It was solely to artificially inflate the commit count, create that visual appearance of intense, ongoing activity. We saw this resulted in massive commit numbers. One repo had close to 60,000 commits generated this way in just a few months. The average across the analyzed repos was over 4,400 commits.
60,000 commits. That's staggering. So they're not just faking stars anymore. They're faking the work itself to look legit and active over time.
Exactly. It's a significant refinement compared to past campaigns that maybe relied more heavily on just dumping fake stars. And beyond the commit automation, the analysis also found striking, consistent patterns across the accounts and repositories that strongly suggest an underlying framework and structure.
What kind of patterns in the accounts?
Several things stood out. The owners of these backdoored repos typically had very few other projects, never more than 9. Often the malicious repo was their only one. If an owner had multiple backdoored repos, they frequently had the exact same first and last commit dates, often the same release dates too. Plus, the number of contributors was consistently low, usually fixed at exactly 3, including the owner. And these contributors seem tightly clustered, associated only with a specific owner's set of malicious repos, not contributing broadly.
Like little dedicated teams of 3 managing sets of these fake projects.
Kind of suggests that, yeah. There were also recurring patterns in the usernames of the contributor accounts across different repos, suggesting they might be auto-generated or pulled from a central pool of accounts.
You mentioned these 3 contributors seem to have distinct roles. That's fascinating.
It really is. In the repos where this 3-contributor pattern was clearest, researchers saw distinct roles. The owner account, often linked to that ishfd83 email, was responsible for the vast majority of commits, like 98.5%, almost all from the automated workflow. The second contributor, usually with a less descriptive username and an Outlook email that looked like random characters, did fewer commits but seemed to be the one adding the actual backdoored file and the main lure code, like the fake RA2 or cheat. And the third contributor, similar username mail pattern, often made only 2 commits, adding the YAML workflow files to the .github workflows directory, including the one for the auto-commit automation.
So one account sets up the automation, another adds the bad stuff, and the owner account just generates noise, and they could figure out the emails for these roles.
Yes, researchers used a technique. Appending .patch to a commit URL can reveal the associated email address. It provided key links. This observed division of labor strongly implies not just automation, but an underlying framework, possibly distinct roles, even if they're automated or managed by a small group.
This level of organization, automation, role division sounds like it could be part of a larger cybercrime business. Does this tie into that concept of distribution as a service, DaaS?
It aligns very strongly with the DaaS concept, yeah. DaaS is a big business model in the cybercrime world. Malicious services, like malware distribution or access to infected machines, are sold to other criminals. It lowers a barrier to entry for less skilled attackers. They can buy access to sophisticated infrastructure and methods they couldn't build themselves. DaaS offerings are all over dark web markets, underground forums, increasingly on platforms like Telegram.
So the operators behind this GitHub campaign, they could be a DaaS's provider themselves, selling this method. Or maybe they're just a customer of an existing DaaS service.
The material suggests this specific campaign is potentially tied to a broader DaaS operation. It shares overlaps with previously reported activity, including campaigns linked to groups known for operating at scale with fake accounts, like Stargazer Goblin noted previously for using over 3,000 fake GitHub accounts. It's plausible the operators here are customers using such a service, or maybe they're a rival DICE provider, or even the same group behind Stargazer Goblin, just evolving their techniques.
And is there concrete evidence that, paid services for GitHub malware distribution actually exist, people advertising this?
Yes. The analysis mentioned finding ads for paid services offering malware distribution via GitHub on a Russian-language cybercrime forum. These ads seem to have been active for years, indicating this isn't just ad hoc. It's a commoditized service in the cybercrime underground.
Given the sophistication, the potential ties to organized cybercrime,
Yeah.
have researchers managed to identify who's ultimately behind this specific campaign? Any names?
Identifying the ultimate actor is always tough. The report suggests limited success in definitively pinning them down so far. But several aliases and clues keep popping up. Aliases like unknown, seen in those Russian comments in the Python script, part of the encryption key, vibe.processByUnknown, the Telegram bot's username, author unconex on paste sites. The name Muck also appeared frequently. Linked to older Discord channels used for Seed 2 in similar past campaigns, seen in staging URLs connected to a site, muckdeveloper.com.
Yeah, any other infrastructure clues, domains, things like that?
Yeah, infrastructure clues like a Telegram webhook domain arturshi.uu, which redirected to octofin.co. WHOIS records for octofin.co listed John Doe in Spain, almost certainly fake. The previous content of arturshi.ru was a site for a social media influencer selling a neural networks course, but researchers found no clear link between that influencer and the malicious activity. Suggests the domain might have been compromised or just conveniently available.
And the paste sites themselves offered leads.
Absolutely. Analyzing pastes on sites like Pastabin revealed activity by a user Ali88Z with paste back to 2023, some linking to older Discord C2 channels using names like Muck and Spidey-Bot. Another user associated with the popcorn-soft.glitch.me paste URL was identified as SearchBRO at Art Product Games. These digital breadcrumbs help connect the dots between this campaign and older similar activities.
So it sounds like this isn't some brand new threat out of nowhere. It's more like a continuation, an evolution of methods seen since at least 2022. Refining techniques, using common components like Electron-specific malware families, paste sites, while adapting the deception, like focusing more on automated commits now instead of just stars.
That's a key point. This is an ongoing dynamic threat landscape. Attackers constantly adapt their tactics to stay ahead of detection and maximize their reach in the open source world.
Okay, so we've detailed the sophistication, the deceptive tactics, the complex infection chains, the organized nature, targeting this wide audience, including savvy folks. Given all this, what can someone actually do? How do we practice effective due diligence in this, frankly, risky open source world?
The absolutely crucial first step is just acknowledging and internalizing the risk we've discussed. As we've seen, anyone downloading, interacting with unverified code from platforms like GitHub is potentially exposed. And those final payloads, the info stealers, the RTs, they're indiscriminate. They don't care if you're a seasoned dev, a security researcher, or a gamer. Run the code that triggers the chain, you're at risk.
So what are the concrete steps? What should listeners be doing differently?
First off, exercise extreme caution with specific categories of repositories. The material explicitly highlighted. Unverified repos claiming to be malware tools, exploits, or gaming sheets are particularly high risk. Known lures for these backdoored projects. Approach anything like that, especially from unfamiliar accounts, with the highest skepticism.
Makes sense. High-risk categories attract high-risk content. But what if it's not an obvious hacking tool or cheat, just a utility, a library, from someone you don't know?
We're practical, especially if you have some technical background. Try to inspect the code before you download, compile, or run it. What to look for. Red flags include big blocks of heavily obfuscated code or strings that are hard to decipher. Be wary of code hidden with excessive white space, like that Python trick requires horizontal scrolling. Look for suspicious calls to external domains, IP addresses. Pay close attention to weird file extensions or file names, maybe using tricks like RLO to look like something else.
Inspecting code can be really time-consuming, though, especially for big projects. What else can help?
Definitely. Do some online research. Search for the repository name online. Has anyone else reported suspicious activity? Analysis results related to that project or account. Use public online tools like VirusTotal. Submit file hashes of executables you find, suspicious URLs from the code. See if they're flagged as malicious by multiple vendors. That crowdsourced intelligence is valuable.
Okay, inspect if possible. Research online. Check files URLs on VirusTotal. What's a fundamental principle to remember when dealing with source code from somewhere you don't know?
This is absolutely critical, worth repeating. Understand that compiling code from an open source repository you haven't fully verified is functionally the same as downloading and running an executable from the internet without knowing what it does. When you hit build, you are explicitly giving permission to execute scripts or commands embedded in the project files, like those malicious pre-build events. You are running potentially unknown code.
Compiling is executing. That's a powerful mindset shift. So if you absolutely must interact with questionable code, what's the safest way?
The single most crucial step for safely testing or examining any potentially questionable code is using isolated environments. Sandboxes, containers, virtual machines, VMs. These environments are designed to be separated from your main OS, your files, your network. They limit the potential damage, prevent malware spreading if the code is malicious.
And if you use an isolated environment, you shouldn't just run it and forget it, right? You need to watch what it does.
Exactly. Simply running it in isolation isn't enough. You need to actively monitor the isolated environment's behavior. Look for attempted outgoing network connections. Where is it trying to talk to? Check if unexpected files are created. Temp directories, user folders, system folders. Monitor for weird registry changes, new scheduled tasks for persistence. Pay attention if security products inside the isolated environment suddenly get disabled, or if there are sudden unexplained resource spikes, high CPU, high memory usage, could indicate malicious activity.
So contain the risk, actively observe. Are there broader defensive strategies that apply here too, beyond just individual repos?
Yes, the general defensive strategies against broader cyber threats and DaaS definitely apply. Maintaining an enhanced security posture is fundamental. Robust endpoint protection, AV/EDR, strong network security, firewalls, IDS, consistent patching, leveraging threat intelligence, staying informed about current threats, tactics, indicators, like by listening to deep dives like this, is key. User education remains vital. Making sure you and others know about deceptive practices, social engineering, supply chain risks. And finally, having and testing an incident response plan. So if something does go wrong, you can react quickly and effectively.
These steps really highlight that while the attacks are complex, informed caution, taking proactive verification steps, can significantly reduce your risk. Put some control back in your hands.
It shifts the dynamic from passive trust to active verification, which is increasingly necessary.
So we've taken a deep dive into this concerning landscape. Threat actors weaponizing code repositories. We've seen the manipulation of popularity and trust signal stars commits, the complex multi-stage backdoors, weaponized build events, hidden code, deceptive files targeting this wide audience, including criminals and researchers. We've unpacked the intricate infection chains obfuscation, leveraging legit services like paste sites and GitHub releases, dropping serious info stealers and RATs. We discussed the evidence of automation, potential ties to cybercrime as a service models, and crucially, covered the essential steps you can take. Cautious inspection, research, isolated environments, monitoring behavior.
Yeah, it's clear that in the open source world, the lines between legit development and malicious distribution are being deliberately blurred. Vigilance and verification are absolutely paramount now.
This threat really highlights a fundamental challenge, doesn't it? For the whole open source community, for individual users. Given how easily trust signals like stars and commits can be faked, how deeply malicious code can be hidden in project files, build processes, even off-screen. What does supply chain security truly mean for individual users and developers just trying to get work done? Can we realistically be expected to manually verify everything, every line, every script, every dependency? Or do we need entirely new models, new tools, new standards from platforms from the community to help establish genuine trust in the code we download and use, especially at scale?
It's a critical, evolving question, needs ongoing attention from everyone involved, developers, users, platform providers.
Definitely something to think about. And thinking about protection in this complex environment, this deep dive was sponsored by Stonefly.
Stonefly, a leader in enterprise storage, backup and disaster recovery, AI storage, and cloud solutions.
If you're looking for secure, ransomware-proof storage, remember, Stonefly offers air-gapped and immutable storage solutions. You can contact sales@stonefly.com to schedule a demo.
And with that, I think we wrap up this deep dive.
Stay vigilant out there, everyone, and keep thinking critically about the code you interact with in the digital world.